All right, so now I'm going to talk about the projection theorem. So previously we've been looking at the use of divergences to measure something like a distance between 2 points on a manifold. Now we're going to start addressing the question of what happens if you have a point and a set on the manifold, and what the appropriate notion of distance is. It's like, is there a sense in which there's a point on a manifold which is the closest? Is there a natural way basically to project it's like a point onto a submanifold or some subset in this information manifold. Okay, so what I'm going to do is I'm going to consider a point P in some smooth submanifold. Let's call it S in a dually flat manifold. M. Okay. Then I can talk about the divergence between a point and this set, or this submanifold. So I can define the divergence from a point P to the submanifold S, right? It's just given by the minimum over points R which are contained in S of P to R. All right, so more generally, it's like you maybe have to think of this as the infimum, right? So basically what you're doing is that you're looking at all possible divergences. It's like between P and some point, it's like on the submanifold S, and you want to find the infimum, it's like of that divergence. And that is, it's like the definition for the divergence, it's like from P, it's like to the submanifold S, right? So this is sort of the usual thing you would expect if you were, say, given some notion of a distance in some space, and you want to then extend that notion of distances between 2 points in that space to a distance from 1 point to some subset of that space. Okay, so this is sort of the natural thing to do. Okay, so once you have that, it's like then you want to, it's natural to find a point, it's like on S, it's like which is the closest in the sense of divergence. So it is natural to consider the question of finding a point in S that is closest to P in the sense of divergences, right? Okay, so put another way, it's like what you're trying to do is to find the arc infimum, it's like of this thing, right? You want to find the R which infimizes, it's like this divergence, it's like between P and R, where R is allowed to vary over all the points, it's like on the set S. Okay. So this is again a very, very natural question. And it's like we study these kind of questions all the time in numerical analysis and approximation theory, right? Where you try to say, for example, take some function, it's like, and then look at maybe a subspace of functions which are generated, it's like by some set of basis functions, and you want to find the closest it's like function, it's like in this finite dimensional subspace to the original function, right? So that's some sort of optimal approximation. It's like sort of projection in the space of functions. Okay. So, so with that in mind, it's like you can define it's like this kind of projection. So we can define the geodesic projection and dual geodesic projection. Of P to S, which is contained in this manifold M. Okay. Then the curve theta of T, right, is said to be orthogonal to S when its tangent vector which is just theta dot of T is orthogonal to any tangent vector to S, right, at any intersection point. At the intersection of theta T with S, right? So let's try to draw a picture of this. Right, you have some sort of curved set. Say, let's call that S. You have theta of T, and you have some sort of intersection point, right? And you have a tangent vector to that, theta dot of T. And this has to be orthogonal to any tangent vector V in the tangent space to S, okay? With the same base point, right? So these things have to be orthogonal. Okay, so that's what we mean by a curve being orthogonal to that space, is that it's orthogonal to all the tangent vectors, it's like to that space. You know, it's like at the point, it's like where the curve intersects, it's like with that set S. Okay, all right, so that's again quite natural. All right, so let's now define this notion of geodesic projection, it's like which we were alluding to. Okay, so let's call that P hat S, right, is the geodesic projection of P to S, okay, when the geodesic connecting P to P hat S, right, is orthogonal to this. Okay, so in this picture, what's happening is the following, right? You have this set S, you have P, which is some point which is in general off the set S, okay, and then you have point P hat of S, and there's some sort of geodesic connecting those two, and this geodesic is perpendicular, is orthogonal to the set S. Okay, so this is what we're going to call the geodesic projection. Okay, it's really an orthogonal projection, if you will. Okay, So, so one has to be a bit careful, right? Because if you recall, there are, when we try to generalize the idea of straight lines to manifolds, there are two different notions of what it means to generalize straight lines, right? Because straight lines, it's like in Euclidean space, satisfy two properties, one of which is that as you move along that line, the tangent vector doesn't change direction, so to speak, right? So that leads to this notion of geodesics in terms of, it's like affine connections, which tell you how tangent vectors get parallel transported along some curve, right? But there's also the fact that the straight line connecting two points in Euclidean space is a length minimizing curve amongst all possible curves connecting inside those 2 points. Okay, and that's a different notion of it's like a generalization of straight line, which involves it's like the metric instead of the connection. So when I define this geodesic projection this way, what I'm really doing is I'm using this notion of orthogonality, right? And in that sense, I'm using essentially the affine connection structure, right, to define what this projection operator is. Okay, so it's going to be related, it's like to this notion of straight lines having to do with not changing directions. Okay, but when we started talking about this projection, we were talking about, it's like the divergence between a point and a set, right? So that is something which is more akin to the notion of distances or length minimization. Okay, so at least on the surface, this is not necessarily related. It's like to the other notion of closest point projection, so to speak. This is orthogonal projection. It's not necessarily closest point projection. So what's going to happen? It's again is the following: is that there is a theorem which says that this kind of orthogonal projection, it's like a geodesic projection, okay, is going to be some sort of length minimization, but not with respect to the original divergence, but it's dual. Okay, so that's going to be what the projection theorem is saying. Okay, so that's where we're headed with all of this. Okay. All right. So anyway, so you have this geodesic projection. It's like, and then sort of the dual of this is that p hat star s is the dual geodesic projection. Of p to s, where the dual geodesic p to p hat star s, which is in S, is orthogonal to S. Okay, so again, it's like the point I'm trying to make here is that at least on the surface initially, we're just defining what is the analog of orthogonal projection, right? There's, at least on the surface, no obvious reason why this solves the other problem which we were interested in looking at, which is to find a point that's like on the set S, which minimizes the divergence between P and P hat S, okay? So that, again, is the content of what is called the projection theorem, which I will now state. So the theorem is projection theorem. Okay, so given some point P on the manifold and a smooth submanifold, S which is contained in M, then the point p hat star of s, which is the dual geodesic projection of p onto s, okay, that is the dual projection, dual geodesic projection of p to s is the point in S that minimizes the divergence. From P to R, where R is in S. Okay, so I should say that I've reworded the theorem slightly. So in Amari's book, he first states the fact that this point, or he first thinks of this point P hat star S as being the point which minimizes this divergence, and then says that this is the dual geodesic projection. But I prefer this statement because we've defined P hat S and P hat star S, it's like as the geodesic projections and dual geodesic projections. So it makes more sense to frame the theorem as saying that P hat star S is the dual geodesic projection, and that point also happens to be the point which minimizes the divergence, right? So there's this interesting, again, duality, right? Because you do your projections with respect to the dual affine structure, but then it's like that point which you get, it's like by dual geodesic projection, is the one which minimizes the divergence as opposed to the dual divergence, okay? So, and you'll start seeing this flavor again and again. It's like in this course in information geometry that you have to go back and forth. It's like between the primal and dual representations, and they're intrinsically sort of connected. It's like in a very, very natural way. All right. And then there's sort of a dual of this, right? So the point P hat S that is the geodesic projection of P onto S, okay, to S, right? Minimizes the dual divergence d phi star P to R, where R is in S. Okay? Okay. So let's try to prove this. It's like, it turns out that this is a relatively straightforward application of the generalized Pythagorean theorem. Okay. So let's see what happens. Okay. So, sorry. So let me try to prove this. Okay, so let P hat star S be the dual dual geodesic projection of P to S. Okay, so what that means then is that you have P to P hat star S, right? And that curve is a dual geodesic. okay, and it is orthogonal. That dual geodesic is orthogonal to the surface S. Okay, so as you might expect, then what's going to happen is that you're going to apply the generalized Pythagorean theorem, right? So you have P, P hat star S, and any other point that's like on the manifold S, on the submanifold S. Okay, let's call that Q. Okay, so Q. All right, so there is some sort of geodesic which connects Q to P hat star S. Okay, so this is a geodesic. Okay, so in particular, a geodesic is a curve on a manifold, so the tangent to the geodesic is in the tangent space to S. All right, so by definition of orthogonal projection, this dual geodesic from P to P hat star S is going to be orthogonal to the tangent to that geodesic. Okay, so now it's like you should see that this is exactly the setting you have. It's like for the generalized Pythagorean theorem, right? So you have a dual geodesic, you have a geodesic, they are perpendicular at a point, and the generalized Pythagorean theorem says that the divergence between P and Q, so by the sort of generalized Pythagorean theorem, the divergence between P and Q is equal to the divergence from P to P hat star S plus the divergence from P hat star S to Q. And you know that this is greater than or equal to 0, and it's only equal to 0 when, so equal to 0 when Q is equal to P hat star S, right? So, so now you know that the divergence from P to Q is minimized, right, when Q is equal to P hat star Q. And Q is any point on S, right? So Q is in S. And, okay, by properties of the divergence function, the right-hand side is minimized when Q is equal to P hat star S. So that means that P hat star S is the arc infimum, right, of the divergence. It's like from P to any point it's like on S. Okay, which is what you set out to prove. Okay, all right. So let me state one final theorem. Okay, so when S is now a special type of manifold, so when S is a flat manifold, flat submanifold, sorry, of a dually flat manifold, M, right, the dual projection of P to S is unique and minimizes the divergence. Then dually so I should say that the reason why we're discussing this is because the projection theorem just gives a necessary condition for it. It's not sufficient, right? So the anyway, yeah. Yeah, so I guess it's like, I take it back. There's a reason why it's like the theorem was stated, it's like the way it was, it's like in the book, because the projection theorem is not an if and only if statement, right? So anyhow, but if S is a flat submanifold, it's like then the two statements are equivalent. Okay, so dually when S is a dual flat submanifold in a dually flat manifold, the projection of P to S is unique and minimizes the dual divergence. All right. I think the main sort of technical reason why it's like you need this additional structure, it's like about it being a flat submanifold, is the following, right? So the argument here, I think that that's fine, but it still relies on one sort of critical assumption, which is that there's a geodesic connecting P hat star S to Q, where Q is any possible point on S, right? So that's not always necessarily the case. It's like, so there's this idea of geodesic completeness. And so you don't, it's like so bottom line is that if Q is very far away, it's like there's no guarantee necessarily that there is a geodesic connecting Q and P hat star S, okay? So, so in essence, it's like what this proof does, right, it is that it shows that this P hat star S is the minimum, it's like over sort of, it's like the geodesically connected component of S containing P hat star S, okay? And so that isn't enough to guarantee it's like that it's the global minimum, right? And so so this additional property that you have this flat submanifold, it's like then means that any point it's like in S is geodesically connected, it's like to this candidate, and then so this argument which we've made, is then a global argument as opposed to a local argument, basically. Okay. All right. So anyway, so let me just stop here for now.